Hello, in this video I'm going to talk about an project. This project, in this project we are going to make an hardware lock or dongle for a Windows application using STM32F429 discovery board, which allows to this Windows application run when we uh, connect our dongle to our computer. Why we use STM32F429? Because STM32F429 discovery board has USB port which could be useful in this project. Also, I should mention that this dongle or USB device doesn't need any additional driver to be recognized by Microsoft Windows. There are some pre-requirements for this project. First of all, you need to know how to work with a USB port. You need to know about USB custom HID device and some related topics. Also, you need to know how to work with STM32 crypto library. Also, you need to know about RSA encryption algorithm and its parameters, including modules, primes, public key, private key. And I should mention that you can learn about above topics on ST website, and there are a lot of useful videos on ST's YouTube channels or MOOC. You can go there and watch some videos about the USB and the crypto library. Because I'm using STM32F4, so I use CM4 library for the crypto library. So in the settings, I should for MCU GCC linker libraries add these libraries, which is STM32 expansion, middleware, STM32 cryptographic lib, and add this library STM32 cryptographic CM4. This is STM32 cryptographic CM4 in this path. I added in this path. Also, I can include the path for the include path of this crypto library. Another notes I should mention that you can generate RSA parameters with different ways. For example, you can use OpenSSL, or you can use your Visual Studio RSI Crypto Service Provider class export parameters function. There is a warning. If you use OpenSSL to generate RSI parameters, don't forget that to remove 00 at the beginning of the generated modules, private exponents, primes, and so on. For example, when OpenSSL generate modules, there is a 00 at the beginning, and you need to remove it. And for example, I correct it like this. This is 00 is because of its sign. So it's important before you use that modules in your program. And another note is related to the RSA crypto service provider, and you want to decrypt or encrypt the message. When you use encrypt or decrypt function, you need to use true. For example, in this function, when I use encrypt function, I send a message and use true. And for decrypt, also like this. Descriptor service provider, decrypt, cipher, bytes, true. It's very important. There is some warning which I want to say. At the beginning, to protect the RSA parameters and the codes on STM32, you need to set readout protection or RDP on level 2 with STMcube programmer. But since this is an educational project, so we won't set RDP on level 2 because we want to only educate these topics. Or you can use other security features to protect your codes and RSA parameters if they're available for your MCU, such as Trust Zone Firewall, OTF deck, picker, and other features. All of these features have been described by Mock on ST's YouTube channel. You can find the related videos on that channel. And about the Windows application code protection, I should alarm that in this educational project, codes and RSA parameters of the Windows application are not protected. For protecting your Windows application, use additional methods and find some way to protect your modules and public key, private key, and something like that. Your application, Windows application codes is not secure in this project. Okay. When we send message from host to the device and the reverse, there is a message which is 64 bytes. First byte is set with 0, and the byte number 1 is set is indicate the length of the message, the length of the packet, and this packet with 62 bytes I have here is composed two parts. Byte number 2 is considered for command. I customized it for command, and from 3 to 63 is considered for data. I indicated here byte 0 is 0, byte 1 is length, byte 2 from 2 to 63 is customized, byte 2 is command, byte 3 to 63 is data. So for sending 256 bytes, we send 4 packets with 61 length and a packet with 12 length, which its total is 256. Why 256? Because the RSA encrypted block is 256 bytes. Like this. I divided these 256 bytes into 5 sections. 4 of them is from 0 to 16, or in the packet from 3 to 63, and there is a 12 byte and a part, fifth part with 12. The conversation between host and the device is indicated here. First of all, I generated the token, which is composed of application ID and a random number. Then I encrypted it with the public key of device. which this encrypted value is from 0 to 255. Then I divide it into 5 sections, and I send this section to the host. I insert each section to the packet, 0 length, and the command is 1, 2, 3, 4, 5, indicate the content of the packet, first part, second part, third part, fourth, and fifth. And these packets are sent to the host, and the device send it back to the host, which indicates its ACK. So in the host, check if the receive number, check if the command number is equal the command number of the received package. Then it send the next part. After receiving all parts of the all parts of the message, they are stored in a like diagram from 0 to 255, and decrypted with private key of device. There is another functionality. There is another operation here which has done with check validity of request. After decryption, we check application ID if application ID is defined by for the device. If yes, the random generated is extracted and encrypt this random number, save it in a 200 in the RS encrypted block, then send this block with 5 packets from 6 to A, 6, 7, 8, 9, A. These codes, these commands, which I described it in this section. For example, 1, first part of the block with 256 parts. 0 to 16 from application. There is a description for all these code, for all this command. However, when I received all this, or when host received all this package, it saves it in the RS encrypted block. It decrypt it with private key of host. A number is extracted and check with Dongle check token. If this random number is equal to the received number, if yes, then open application and open the lock. For MCUs, there is a state machine. When it's started, it goes to the wait for request and wait for the request from the host. If there is an error, it stay here, and then packets 1, 2, 3, 4 parts of the message is received, it still here, stay here. But when fifth part of the message, fifth part of the request is received, then it goes to the process request and try to request and decrypt, check the validity, and encrypt the message. But if there is an error or an unverified message, it returns back to the wait for request. But if the decryption, check the validity, and encryption has done successfully, then process done and go to the response and try to send this encrypted number to the host. When it sends the first part, second part, third part, fourth part, they stay in this state. By sending the fifth part, it go back to the wait for request for waiting another request if there is. The cause of state machines are here. This state machine is used in the while loop of the MCU. If in that while loop, if wait for request or when it response, there is nothing to do. But if we are in the process request, we should decrypt the message, check the validity of the request. We should these operations. Decrypt the message, check the validity of the request, encrypt the response, go to the response mode and send the first part of the response to the host. But if there is any problem, it go back to the wait for request. Okay, there is a function which we call check dongle log in the Windows application, the host computer. I describe it here. This is exactly this part, but I say it again. There is an application ID, for example, ABCD 12345. I make a token with this application ID and a random number, decrypt it with the public key of the device, set in the encrypted RSA message, and try send these parts. Send part 1, part 2, part 3, part 4, part 5. Every time we send it successfully, it goes to the next part. After the fifth part is sent successfully, we exit from the send request. Then it waits for the response. First of all, it waits for the response first part. And in this part, in this first part, in this section, it increases timeout value for it because RSA encryption or decryption operation is time consuming, and it may take a long time. So in this section, I have increased the timeout. After passing this part, we go to the second part, third part, fourth part, fifth part, and wait for this response. After we receive the fifth part, we exit from this. We have the message here, and decrypt with private key and check it with this random number. The codes are here. We create a token, encrypt it with public key, and check the connectivity of the device, USB device. Then send the request, wait for the response first part, and finally, when we received all the parts, we try to decrypt it with the private key of the host, that encrypted RSA message, and check the token.